Today I'll be talking about binary search trees and how to perform insertion and deletion operations on this type of tree. A binary search tree, often called a BST, is a data structure which allows us to insert, delete, and search elements in linear time. A binary search tree is a binary tree which follows an additional BST property. That is, each node has at most two children nodes, and that for every node x in the tree, the subtree to the left contains nodes with values less than x, and the subtree to the right contains nodes with values greater than x. Due to this BST property, the nodes in a binary search tree are sorted. So a list of elements in ascending order can be formed by performing an in-order traversal of the tree. Searching for any element in a BST is simple. Starting at the root, if the value of the current node is less than the value we are searching for, we traverse down the left subtree, and if it is greater, we traverse down the right subtree. Then, repeat until we find the node with equal value, or until we reach a non-matching leaf node, meaning the search was unsuccessful. It is apparent that this operation will take linear time, as in the worst case all nodes in the tree are visited. Inserting into a BST is very simple. We traverse down the tree until we find the appropriate node and append the new node as a right or left child, depending on the BST property. Let's insert some nodes into this tree. Deleting nodes from a BST may be tricky, as the tree may disconnect and we would have to maintain the BST property after deletion. We can consider three cases for deletion. First, if the node we want to delete is a leaf node, we simply delete that node. Second, if the node we want to delete has one child, we promote that subtree to the place of the deleted node. Third, if the node we want to delete has two children, we need to be careful about how we maintain the BST property after the deletion. To delete a node x, we want to find a node y such that y is the node with the minimum value of the right subtree. This is called a successor, so y is the successor of x. To get the intuition behind this method, we need to convince ourselves of the fact that the successor of a node will never have a left subtree. This is because the successor is the node with the minimum value, and any node that goes to the left means that that node has a smaller value, which contradicts the successor status of the node. In the case that the successor y is directly connected to x, we simply delete x and promote y to x's original position. But if y is not directly connected to x and is located somewhere else in the right subtree, we need to relocate y so that it is directly connected to x, then perform the same deletion process as before. So to continue with the deletion, we would need to remove the successor node y and promote y's right subtree in its place. Since y has the minimum value in x's right subtree, all nodes in X's right subtree have values greater than Y, so we can make X's right subtree Y's right subtree and delete X. This way, the node is deleted effectively and the BST property holds after the deletion. Let's illustrate this method with some examples and delete some nodes from this tree.